Okay, let's unpack this. Think about the raw power of the sun for a second.
Mm-hmm.
It's the engine of our entire solar system, obviously, but it also throws off these incredible bursts of energy, solar flares that can actually reach out and touch us here on Earth.
Right, disrupting satellites, messing with power grids.
Exactly, even scrambling radio communications. But then, on the flip side, these same events can trigger these absolutely stunning auroras, those shimmering curtains of light.
Sometimes appearing way further south than you'd ever expect.
Yeah.
What's truly captivating, though, is that we've recently had an unprecedented opportunity to witness one of these dramatic solar events in incredible detail, all thanks to a brand new perspective.
Exactly. That's what we're diving into. A major solar flare classified as an X6.3, and that X rating, well, that means it's one of the most powerful categories.
Top tier, yeah.
It happened back on February 22nd, 2024. But what makes this deep dive so compelling isn't just the size of the flare, it's the groundbreaking way we observed it.
That's right. Our focus today is on the data captured by Aditya-L1.
India's recently launched solar observatory.
Yep. Took to the skies in 2023 and strategically positioned itself at the L1 Lagrange point.
Ah, that gravitational sweet spot between Earth and Sun.
Exactly. And crucially, it was equipped with a suite of 7 scientific instruments, all, primed and ready for significant solar activity.
So our mission for this deep dive is to really get under the skin of this powerful solar flare using the unique eyes of Aditya-L1.
We want to understand its origin story and how it evolved.
And explore the brand new insights this data is providing us. Our main sources detail Aditya-L1's capabilities and give us the lowdown on its observations of this specific X6.3 event.
Okay, so let's start by appreciating the sheer intensity here. An X6.3 class solar flare.
These are the heavyweights.
Definitely. The ones that carry a real punch and have the potential to cause significant disruptions to our technology here on Earth, just like you mentioned. Satellites, power grids.
Absolutely. And this wasn't just a flash in the pan, right? This event peaked around 22.34 Universal Time on February 22nd, 2024.
And the entire eruption lasted for about 35 minutes.
What's also interesting is that it didn't just appear out of nowhere. It originated from a specific active region on the sun's northern hemisphere.
Within a group of sunspots. So the location itself gives us clues about the underlying magnetic activity driving this whole thing.
Now, this is where Aditya-L1's strategic location truly shines.
Right. While we have other solar observatories, Aditya-L1 sits way out there, about 150 million kilometers from the sun.
Basically right in the firing line.
Pretty much. Now compare that to, say, the European Space Agency's solar orbiter. It also got valuable data here, but it orbits much closer, around 42 million kilometers sometimes.
Okay, but here's where it gets really interesting. That greater distance for Aditya-L1 actually offers a unique advantage.
How so?
Well, when it comes to seeing where these flares begin, our sources emphasize that it captured the very first images of this solar flare erupting from the lowermost layers of the sun's atmosphere.
Specifically the lower chromosphere.
Exactly. Think of it like being able to see the initial spark, the first flickers of the flame. It's a perspective that's incredibly difficult for other observatories to get with the same clarity, especially from closer in. Why is seeing that origin point so significant?
Well, it's a fundamental shift in how we study these events. To understand why, picture the sun's atmosphere as layers.
Okay.
You have the visible surface we see, the photosphere. Then moving outward, you hit the chromosphere, this really dynamic region.
Right.
And finally, the corona, that incredibly hot, wispy outer layer you see during eclipses.
Got it.
So when a solar flare ignites, it doesn't just pop into existence fully formed. It travels, it propagates outwards through these different layers.
As it pushes through, it changes, right? The type of energy it emits.
Precisely. It starts off maybe as mostly visible light near the surface, then transitions to ultraviolet radiation as it moves up into the chromosphere, and ultimately blasts out as X-rays from the superheated corona. We're talking temperatures over 1 million degrees Celsius up there.
That jump in temperature is just staggering. From about 5,800 degrees at the surface to over 1 million. What does that tell us about the forces involved?
Well, what's fascinating here is the scientific consensus. It points to the sun's constant release of magnetic energy as the driver for this extreme heating.
Magnetic energy?
Yeah, think of the sun as this huge magnetic dynamo. It's constantly twisting and tangling its magnetic field lines.
Okay.
When these lines suddenly snap and reconnect, a process called magnetic reconnection, they release vast amounts of energy. Solar flares are one of the most dramatic results of that.
Now, Aditya-L1 wasn't just watching passively. It's got specialized tools to dissect this whole process.
Absolutely. And one of the key instruments for this particular observation was the Solar Ultraviolet Imaging Telescope, or SU.
SU. Okay.
What makes SU so remarkable is its specific focus. It's designed to detect long-wave ultraviolet light in the 200 to 400 nanometer range.
And that specific range is important
because that particular sensitivity allowed it to peer directly into that lower chromosphere, the very birthplace of the solar flare, with unprecedented detail.
So it's like having a new kind of vision. It lets us clearly see a layer that was maybe hazy or indistinct before, at least from afar.
Exactly, especially with this kind of resolution.
And this flare on February 22nd was the perfect test case for SESORT. Our sources even mention it captured the flare using all 8 of its different filters. That sounds complex. What does using multiple filters actually give you?
That's a great question. Think of each filter as being sensitive to a slightly different slice of that ultraviolet spectrum.
Okay.
And these different wavelengths of UV light, they're emitted by the solar plasma at different temperatures and densities within the sun's atmosphere.
Right.
So by observing the flare through these 8 distinct filters, basically simultaneously, scientists can create a multi-layered map of the flare's properties right at its origin.
A map showing
Temperature.
density.
Yeah, its temperature profile, its density, and crucially, how these change over time and across different spots within the flaring region. It gives us a much richer, more comprehensive picture than just one single wavelength could.
So it's like seeing different facets of the flare all at once.
Yeah.
Very cool.
Yeah.
And it wasn't just SUI providing this crucial information, was it? I remember reading that data from another instrument on Aditya, the Solar Low Energy X-ray Spectrometer, SOLIC-S, was also important.
Absolutely. They work together. While SUI was giving us this detailed UV view of the lower atmosphere,
The birthplace.
so LAXS was simultaneously tracking the higher energy emissions, the X-rays, the stuff associated more with the flare as it gets hotter and particles get accelerated up in the corona.
Okay. So SUI sees the spark and SOLIC-S sees the resulting explosion higher up.
In a nutshell, yeah. It allows scientists to directly connect that initial eruption in the chromosphere with the subsequent heating and particle acceleration in the corona.
So they're essentially getting this multi-wavelength picture, piecing together the flare story from its very beginnings all the way up into the sun's outer atmosphere.
Precisely.
And it wasn't solely reliant on Aditya-L1, though. The team also incorporated data from other eyes in the sky, like NASA's Solar Dynamics Observatory and ESA's Solar Orbiter, plus telescopes on the ground. It sounds like a truly global, collaborative effort to understand this one event. What did bringing in those different data sets add?
Well, by integrating data from all these different viewpoints and instruments, scientists could get a much more holistic view.
Okay.
For instance, while Aditya-L1 was zeroed in on the flare's initiation with SU-80,
Right.
Solar Orbiter, being closer, could provide maybe complementary high-resolution images of the flaring region at slightly later stages or from a different angle.
Different perspectives.
Exactly. And SDO, with its wide range of instruments, offers context about the overall magnetic environment on the sun at the time. Ground-based telescopes might have tracked effects in Earth's atmosphere or provided other details about the active region.
So it's like having multiple witnesses to the same event, each with their own specialty.
That's a good analogy. Each brings a unique piece to the puzzle.
And by combining all these perspectives, the researchers arrived at a really key finding, didn't they?
Yeah.
Something about the connection between what Ceci saw happening low down
Atmosphere.
and the temperature spike way up in the corona. That sounds like a crucial link in figuring out how these flares actually work.
It is. It's a critical piece of the puzzle. This direct correlation they observed shows pretty clearly that the energy released down low during the flare is directly responsible for that extreme heating we see higher up in the corona.
So it helps pin down how the energy actually travels and gets dumped into the atmosphere during these eruptions.
Exactly. It helps us understand the mechanisms of energy transport and dissipation.
And Sami Solanki, a director at the Max Planck Institute for Solar System Research, one of the co-authors, he really stressed how significant this was. He called it a real stroke of luck that Aditya-L1 was there, ready, to see such a powerful flare so early in its mission.
Fortuitous timing, for sure.
And crucially, he pointed out how this data, especially when combined with the other observations, gives us For the first time, a complete picture of the processes that occur in different layers of the solar atmosphere during a flare. That's a pretty big claim. What makes having this complete picture so important?
It's transformative because, well, for a long time, our understanding of solar flares was somewhat fragmented.
Like snapshots from different places without knowing how they connected?
Kinda, yeah. We could see effects in the corona, we could see some things lower down, but linking them definitively, especially during the flare's onset, was tricky. This new data from Aditya-L1, especially from Sept, provides that crucial link from the lower chromosphere right up to the corona. It lets us build a much more coherent and comprehensive model of how these incredibly energetic events actually start, how they evolve, and how they release all that power.
So moving beyond just describing what happens to understanding the physics behind it.
That's the goal.
And ultimately, the big hope here, the reason this is so important beyond just understanding the sun, is that this deeper, more complete picture could pave the way for better predictions.
Exactly. More accurate predictions of when these flares might erupt, how intense they might be, and importantly, what their potential knock-on effects here on Earth could be.
Which brings us back to safeguarding our vital technology. The satellites we rely on for GPS, for communication.
Tower grids, air travel communication systems.
All vulnerable to these powerful solar outbursts. So better prediction means better protection.
That's the long-term aim. And it's worth remembering that Aditya-L1 is a flagship mission of the Indian Space Research Organization, ISRO. Its success in capturing this data so early on is a real testament to their growing expertise and capabilities in solar and space science. A huge achievement for them.
And it's also fascinating to see the international collaboration behind this specific instrument, SUIT. Our sources point out it was initially conceptualized by the Max Planck Institute in Germany.
MPS.
But the actual design, build, the whole construction was led by the Inter-University Center for Astronomy and Astrophysics, IUCAA, in Pune, India.
And IUCAA also led this particular publication we're discussing.
It's a fantastic example of scientists from different institutions, different countries working together. We even had, 3 scientists from Max Planck on the SUIT team itself.
Yeah, it highlights how modern space science is often a very collaborative venture. You need expertise from all over.
Definitely. And for those listening who want to dive even deeper into the specifics.
The paper itself.
Yeah, these findings were published in the Astrophysical Journal Letters. The date was February 28th, 2025. The title is Near and Mid-Ultraviolet Observations of X6.3 Flare on 2024 February 22, recorded by the Solar Ultraviolet Imaging Telescope, onboard Aditya-L1, lead author Soumya Roy, and the team.
And if you really want to find it, the DOI, that digital object identifier, is 10.384720418213ADB Should get us straight to it.
Perfect. So to wrap up this deep dive, it's really clear we've witnessed a pivotal moment in how we study our sun. Aditya-L1, this new solar sentinel,
has given us an absolutely critical and, as the sources keep stressing, an unprecedented look at the very beginnings and the early development of a major solar flare.
That unique ability of the SUIT instrument to see the lower chromosphere with such clarity. It's genuinely groundbreaking.
It really is filling a long-standing gap in our observational toolkit. It's allowing us to probe this crucial region of the sun's atmosphere with a level of detail we simply haven't had before.
Which just opens up so many exciting new questions and avenues for future research. And this all leads you, the listener, with a really compelling question to think about. Considering this brand new level of detail we can now capture from the sun's lower atmosphere, what other secrets might this incredibly dynamic region be holding? And maybe more practically, how might this deeper understanding of solar flares, right from their birth, ultimately help us better protect the increasingly complex technology and infrastructure that our modern world relies on every single day?
It really underscores the ongoing and, vital quest to unlock the many remaining mysteries of our nearest star. Still so much to learn.